What if the most heavily defended supply route in the Middle East, the one Iran spent years hardening, protecting, and treating as untouchable, was destroyed in less than 30 seconds of coordinated airstrikes, and Iran never saw it coming until the mountain was already falling? That is not a dramatic exaggeration. That is what happened in the early hours of a single morning when American stealth aircraft, cruise missiles, and decades of engineering precision came together to sever the one logistical artery Iran feared losing above everything else. The dust cloud was visible from the docks miles away, and by the time the sound reached the port city below, both roads out of Iran's largest harbor were gone. If the mechanics of modern warfare, the real tactics, the real technology, the real decision-making behind operations like this, are what you come here for, subscribe right now and hit the notification bell. Like this video if you want this channel to keep going deeper than the surface coverage, and share it with someone who wants to understand not just what happened, but exactly how it was done and why it worked when Iran's defenses should have stopped it. Because the answer to that question is more interesting than most coverage has bothered to explain. Let's get into it. To understand why this operation mattered so much, you first need to understand what was at stake geographically. Bandar Abbas is Iran's largest and most strategically critical port. It sits at the mouth of the Strait of Hormuz, the narrow choke point through which roughly 20% of the world's oil supply passes. Everything moving in and out of Iran by sea passes through this city: container ships, fuel tankers, military supplies, commercial goods. The economic and logistical heartbeat of a significant portion of Iran's economy flows through Bandar Abbas. And north of that port, the terrain creates a problem that no amount of money or engineering can fully solve. A mountain ridge runs across the route that every truck, every fuel convoy, every supply shipment must use to move cargo from the port northward into the country's interior. That ridge doesn't have many gaps. In fact, for practical purposes, it has two. One road threads through a tunnel carved directly through the mountain, the Shahid Miri Tunnel. The other loops around on a longer inland route crossing the Rukn Bridge. Two roads, two ways north from Iran's most important port. That's it. Pull one screw out of a hinge and the door hangs useless. Destroy both pathways and everything moving through Bandar Abbas stops. Not slows, stops. Every container bound for the interior, every fuel truck, every piece of military supply destined for forces that were supposed to be unreachable by air attack. The entire supply chain serving 1/4 of Iran's economy suddenly has nowhere to go. This is the target Iran spent years protecting. This is the supply line they feared losing above all others. And the Americans knew exactly why. Planning an operation against this target wasn't simply a matter of choosing the right bombs and pointing aircraft in the right direction. The challenge was reaching those targets at all. Through an air defense network, Iran had spent years and hundreds of millions of dollars building specifically to prevent exactly this kind of strike. Understanding how that defense network worked and how the American operation was designed to defeat it layer by layer is the real story here. Iran's air defense along its southern coast is built in depth. Not a single wall, but multiple overlapping layers, each designed to catch what the previous layer missed. At the outermost edge sits an over-the-horizon radar system, a type of installation that bounces its signals off the ionosphere and receives reflections from targets far beyond the normal curvature of the Earth. The claimed detection range stretches to approximately 1,800 miles. That's the distance from one coast of the continental United States to roughly the middle of the country. Continental scale coverage from a single installation. That sounds impenetrable. It isn't, for a specific and important reason. Detection range at that scale comes with a severe cost and precision. A radar contact at maximum range might be accurate to within 20 or 40 miles. The system refreshes roughly twice a minute. By the time that information travels through communication links and reaches a commander's ears, it has already aged. The over-the-horizon radar can tell an air defense officer that something is moving through a general sector. It cannot give him the precise, continuously updated track he needs to actually shoot something down. It hands off a rough location to the closer range systems and asks them to finish the job. And this is where the geometry of the American strike plan begins to pay off. The attacking formation consisted of 4 aircraft. 2 F-35A stealth fighters carrying their weapons sealed inside internal bays where nothing external betrayed the presence of ordnance, and 2 F-16CJ Wild Weasel variants riding escort, armed with a very specific mission that would prove decisive in the minutes ahead. The formation launched its attack run from over the Gulf, flying at extremely low altitude, in some accounts barely 50 feet above the water, to stay below the radar horizon of coastal installations for as long as possible. No radio transmissions, no active radar missions from the attacking aircraft. Just 4 jets burning fuel in the darkness and silence, heading north at better than 500 knots. The over-the-horizon system caught a faint contact, not the fighters. The tanker they had used for the final fuel transfer sitting further south was visible. The radar operator saw it. He picked up a phone. He reported that American aircraft were somewhere in the general area, and that information began its slow journey down through Iran's communication chain toward the coastal air defense batteries. On a ridge overlooking the coastline, an S-300 PMU-2 battery received the alert and went active. This is Iran's best long-range surface-to-air missile system, a Russian-supplied weapon NATO designates the SA-20 Gargoyle. Each missile weighs roughly 2 tons. It flies faster than Mach 6. It can engage targets at significant range. Against a conventional fourth-generation fighter, this system is genuinely dangerous. The engagement radar began sweeping the sector. The crew was professional, prepared, and doing exactly what their training required. They just couldn't find the aircraft they were looking for. Here is why the F-35 creates a problem for radar systems that goes beyond simple stealth. The aircraft doesn't become invisible in the way the word invisible suggests. What it does is more precisely described as arguing with the radar. Every surface angle on the airframe, every panel seam, every edge of every control surface is designed so that when radar energy hits the aircraft, almost none of it bounces back toward the radar dish. Instead of a clean, strong return, the kind that lets a radar operator build a confident track and develop a firing solution, the F-35 returns a signature roughly the size of a golf ball, faint, inconsistent, the kind of contact that might be a bird, might be clutter, might be a ghost in the system. That small signature doesn't give the battery enough to confidently shoot, but the crew could see something faint and low and fast, flickering at an aspect angle their briefing said wasn't supposed to happen. The battery commander made the professional decision. Take the shot he had with the information available. A missile launched, it roared off its rail, accelerated to speeds that make a rifle bullet look sluggish, and flew toward the last known position of the contact. A weapon costing $1.5 million reached the intercept point and detonated over open water miles behind the formation, which had executed a hard climbing turn at the right moment. The warhead found nothing but morning air. The S-300 battery began its reload sequence. The engagement radar kept transmitting, searching, sweeping, trying to rebuild the contact it had lost. That transmitting radar dish was about to become the most dangerous thing on the ridge, but not in the way the crew expected. Now, before we get into the part of this operation where the American formation begins systematically dismantling Iran's defenses from the inside out, let's do something. If you've made it this far and you're finding this breakdown genuinely useful, here's what I want you to do. Go to the comments right now and tell me which part of this operation surprised you most. The stealth geometry, the radar physics, the coordination between different aircraft and weapon systems. Drop it below. I rate everything posted there. And if you haven't subscribed yet, this is the moment. Because what happens next involves a weapon that hunts radar dishes using the radar's own transmissions. And the physics of how that works is one of the more remarkable things in modern warfare. The 2 F-16 Siege escorts had been listening since before the coastline appeared on their instruments. Under each aircraft hung a targeting pod called the HARM targeting system, a passive sensor that doesn't transmit anything but continuously receives and analyzes radar emissions from every source in the environment. As the formation flew north, these pods were silently drinking in every pulse from the S-300's engagement radar on the ridge above, comparing the timing of pulses received by both aircraft, triangulating, squeezing the radar's location from 2 different angle measurements until the position resolved to a box small enough to put a weapon inside. The S-300 radar had been announcing its own location with every sweep of its dish. Now that announcement had an answer. A HARM missile left the pylon of one of the F-16s and accelerated toward the ridge at better than Mach 2. The AGM-88E HARM is a weapon with a specific and ruthless logic. It follows the radar transmission back to the antenna the same way you might trace a telephone call back to the person making it. It doesn't need to see the radar dish. It doesn't need its own targeting data. The dish provides all the guidance the missile requires by the simple act of operating. There was a race now, the HARM flying toward the ridge, the S-300 battery completing its reload sequence, a second missile rising onto its launcher rail, 40 seconds of missile flight time against a roughly 60-second reload cycle. The battery crew had no idea any of this was happening. They were heads down on their instruments, running the reload procedure they had drilled hundreds of times, watching a fresh contact appear on their scope, working the problem the way professionals work problems. The HARM hit the engagement radar. A bloom of dirt and shredded antenna panels spread across the hilltop. The S-300 launcher, with a fresh missile now sitting on its rail, was suddenly the most expensive piece of useless hardware on the Iranian coast. A surface-to-air missile system without a functioning engagement radar cannot shoot, it cannot track, it cannot guide a weapon to a target. The launcher was operational, the missile was ready, and there was nothing to aim it at. A weapon worth roughly $30 million in radar infrastructure, destroyed by a missile costing just over $1 million, and no spare engagement radar existed to replace it on this stretch of coast. But the air defense system didn't simply collapse with the loss of one radar. Iran had built redundancy into its communication architecture for exactly this reason. Buried fiber optic cables and microwave relay stations connecting the over-the-horizon radar's general contacts to the batteries scattered along the coast. Giving those batteries a head start when contacts were approaching, cut the relay and the batteries fall back on their own sensors, defending smaller airspace with slower reaction times and no shared picture of what else is happening across the sector. A Tomahawk cruise missile launched from a U.S. Navy destroyer in the Gulf had already addressed that relay problem, the BGM-109. Tomahawk doesn't need a human guiding it in real time. It navigates by matching the terrain beneath it against a stored map, flying at low altitude the entire route, checking its position against the actual landscape every few seconds, and making corrections. It's described as flying a road it has memorized. The guidance doesn't require sight in normal conditions because the memory does the work that sight would otherwise do. The communications hub that served as the main relay for coastal air defense traffic had taken a Tomahawk through its roof before the attack formation reached the coastline. When the Iranian sector commander reached for his phone to coordinate with the batteries under his command, he heard nothing but static on both primary and backup circuits. The network was still alive in fragments. The over-the-horizon radar was still transmitting its twice-a-minute contacts through military phone lines to Tehran and back down to individual units. But those units were now islands, each one defending its own small piece of sky without the shared picture that makes a layered air defense network function as a system rather than a collection of isolated positions, which is when the next layer of Iran's defense found the formation in a way nobody had anticipated. A Tor M1 short-range air defense system, NATO designation SA-15 Gauntlet, was parked at a fuel depot along the attack corridor. This system carries its own search radar, its own tracking array, its own missiles, all on a single-tracked vehicle that needs no external communication to function. It doesn't need a phone call from headquarters. It doesn't need a data link from a central radar. It scans the sky around it, builds its own picture, and shoots on its own authority. When the S-300's engagement radar went down and the relay station went silent, this system kept working because it had never relied on either of them. The formation flew straight into its coverage bubble. A lock tone screamed in the lead pilot's headset, 8 missiles in their racks, a detection range reaching out 17 miles in every direction. Reaction time measured in seconds. Against most aircraft, this engagement would be over before the pilot could formulate a response. The lead pilot didn't brake. He didn't deploy countermeasures. He didn't maneuver violently to try to defeat the lock. He flew straight and steady through the heart of the Tor's engagement envelope and waited for his aircraft to handle the problem. Because the F-35 doesn't fight radar systems only by being hard to see. It also fights them by lying to them. Built into the aircraft's wing, leading edges, and tail surfaces are the apertures of an electronic warfare system that processes every radar emission hitting the airframe in real time. When the Tor's tracking radar sent out a pulse and received an echo from the aircraft, the system sampled that incoming pulse, held it in digital memory for a fraction of a second, modified it slightly in frequency, amplified it, and transmitted it back, louder and cleaner than the real echo. The Tor's tracking system, programmed to lock onto the strongest, cleanest return, grabbed the manufactured lie instead of the real reflection. And then the system began walking that false return gently off the aircraft's actual position, pulling the tracker's attention away centimeter by centimeter until the lock was chasing a point in space that had nothing behind it. The Tor operator watched his track jump, accelerate in a way no aircraft can actually move, and vanish from his scope. He held his fire. Doctrine is clear. Don't waste missiles on a corrupted track. Reacquire and confirm before shooting. He began reacquiring. The formation was already past him. Now came the final technical problem, finding the specific target with enough precision to actually destroy it. The Shahid Miri tunnel doesn't have a broad, obvious profile when viewed from altitude. It has portals, specific points on a mountainside where the road disappears into rock. Miss those points and a 2,000-pound bomb hits granite, the mountain absorbs the blast. The road survives. The operation fails. The F-35's APG-81 radar solved this using a mapping technique that turns the aircraft's own flight path into an antenna. Flying past a fixed point on the ground while the radar stares at it allows the system to add up all the Doppler information generated by the relative motion and build an image far sharper than any instantaneous snapshot could produce. The longer the flight path, the longer the effective antenna, the sharper the resulting image, sharp enough to distinguish poured concrete from natural rock face, precise enough to hand targeting coordinates accurate to within a few yards, directly to the weapons. Those coordinates flowed into the guidance systems of 4 GBU-31 JDM penetrator bombs. 1-ton weapons built differently from conventional bombs in a specific and important way. A standard large bomb is mostly explosive material inside a relatively thin metal case. The GBU-31 penetrator reverses that ratio. Over 1,300 pounds of forged hardened steel wrapped around 500 pounds of high explosive. The thick steel case is what allows the weapon to survive the initial impact with reinforced concrete or rock and keep moving before the fuse fires. Not on impact, 10 seconds after impact. deep inside whatever it has punched through. Time on target was the final element. Both portals of the tunnel, the western entrance and the eastern exit, had to be struck simultaneously. Not nearly simultaneously, within the same fraction of a second. Because a weapon hitting the western portal gives anyone watching the eastern portal 2 seconds of warning, enough to begin emergency procedures, enough to potentially close blast doors, enough to complicate the operation in ways the planners had specifically designed to avoid. Surprise is a force multiplier. Synchronized surprise is a different category of problem entirely. Each aircraft's weapons computer worked backward from a single designated moment, the time on target, accounting for the bomb's glide characteristics, the wind data passed from the tanker crew during the refueling, the aircraft's speed and heading, and the distance remaining to the release point. Release this bomb from this position at this speed, and it arrives at that coordinate at that exact second. All 4 weapons solving for the same final moment from 4 different starting geometries. The weapons bay doors were the last vulnerability. Open weapons bays on an F-35 turned the aircraft's carefully managed radar cross-section from a golf ball into a barn. The empty interior of the bay reflects radar energy directly back toward any dish pointed at it. 3 full seconds to swing open, 3 seconds of exposure. The pilot watched the Tor's search antenna complete its sweep, confirmed the beam was moving away, and opened the bays in the gap between sweeps. 4 weapons fell free. The doors closed, the formation banked hard south and ran for the coast while the bombs flew the rest of the route alone. 50 seconds of guided glide. The jets were already miles behind the coastline heading for the tanker when the first penetrator arrived at the western portal and drove itself into the reinforced arch above the tunnel entrance. The fuse held for a fraction of a second, long enough for the weapon to travel tens of feet past the arch and into the roadway before detonating. The blast had nowhere to go. A 2-lane concrete tube doesn't allow a pressure wave to expand the way open air does. The shock front raced inward from both ends simultaneously, meeting somewhere near the middle and briefly stacking, a firecracker inside a pipe rather than a firecracker in the open. The reinforced arch, built to support the enormous compression of a mountain pressing down from above, was not designed to resist an explosion pushing outward from below. It failed at a fraction of its rated strength and folded onto the roadway with the mountain riding down behind it. Both portals collapsed into dust and debris within the same second. The ridge that was supposed to be the tunnel's protection became the lid on a pressure vessel that had just ruptured. The dust cloud rose in the first sunlight of the morning, visible from the docks of Bandar Abbas far below, right on the timeline the mission planners had written months earlier. While the tunnel dust was still rising, Tomahawk missiles from the same destroyer found the Rukn Bridge on the inland route. The bridge folded into its riverbed, both roads north from Iran's largest port. Gone inside 3 minutes. Every container ship in harbor that had been loaded and waiting. Every fuel tanker queued up for the northbound convoy. Every military supply shipment intended for forces that had been presented to the Iranian public and to the region as protected and unreachable. All of it sitting behind a severed supply chain with nowhere to go. Routes that would normally take hours now required detours measured in days or weeks, if they could be made at all, given Iran's limited alternative road infrastructure in the region. The implications extended beyond the immediate logistics disruption. The supply line Iran had specifically prioritized protecting, the one they hardened, defended, and invested years of military planning into securing, had been severed in the time it takes to eat breakfast. The air defense network surrounding it, built at enormous expense and maintained with considerable professional competence, had been defeated not by brute force, but by a sequence of precisely targeted technical and tactical advantages, stacked one on top of another. The over-the-horizon radar saw something, but couldn't tell anyone exactly where it was. The S-300 battery shot and missed because the aircraft's radar cross-section compressed the engagement geometry beyond the system's ability to build a reliable track. The harm found the S-300's engagement radar through its own transmissions and destroyed it. The Tomahawk severed the communication relay that would have coordinated the remaining defenses. The Torzlok was defeated not by evasion, but by the aircraft's own electronic warfare system, substituting a manufactured lie for the real radar return. And when 4 weapons arrived at 2 portals within the same fraction of a second, there was no warning, no preparation, and no second chance. This is what the collision of stealth technology, precision guidance, electronic warfare, and careful mission planning actually looks like when it's executed without error. Not a single dramatic capability doing everything. A sequence of interlocking advantages, each one solving a different part of a problem that would have defeated any one of them alone. Iran built its defenses assuming that any attacker would have to fight the system as it was designed to be fought. Engaging radars that were transmitting, shooting at emissions that could be tracked, facing an adversary who couldn't suppress multiple layers simultaneously. What they faced instead was a formation designed from its first principles to defeat each layer before the next layer could be warned. a system designed against conventional threats, meeting an attack built specifically around the gaps between those threats. The guide who made it possible wasn't present in any of the cockpits. He existed in the design offices that spent decades arguing about panel seams and radar angles, in the signals intelligence analysts who mapped the communication architecture between the over-the-horizon system and the coastal batteries, in the mission planners who worked backward from a single desired second of simultaneous detonation to determine exactly when each aircraft needed to be at exactly which point in the sky, in the engineers who built a fuse delay precise enough to guarantee that a weapon traveled far enough inside a concrete tube before detonating to turn the tube itself into the amplifier. None of that shows up in the footage of dust rising above a mountain ridge, but all of it is what made the dust rise on schedule. For Iran, the loss was strategic as much as physical. The supply route they had prioritized above others was gone. The defenses they had relied upon had failed. And the message delivered to every military planner watching this conflict closely, every government assessing whether its own air defense architecture could withstand a similar operation, was specific and uncomfortable. Expensive systems operated by professional crews following correct doctrine can still be defeated when the attacking force has spent decades engineering solutions to every layer of the defense in advance. The mountain didn't protect the road. The mountain became the weapon that destroyed it, turned into a pressure vessel by the geometry of the attack. And the dust cloud that settled over those collapsed portals was visible from the harbor below, from the very port that the road was supposed to have protected. 30 seconds of ordnance, 30 years of preparation, and a supply line that Iran feared losing above everything else, gone before the morning shift at the docks had finished their first cup of tea. That is what overwhelming precision looks like when it commits to a single, focused objective, and that is the operation that severed the one artery Iran had spent years believing was safe. If this breakdown changed how you understand what modern military operations actually look like beneath the surface, the layers of technology, planning, and execution that never make the headline but determine the outcome, share this video somewhere specific, not just a like. A deliberate share to a forum, a group, a place where people who want to understand this level of detail are actually looking for it. That single action puts this analysis in front of the audience it was built for. Share it, stay subscribed, and I'll see you when the next one drops.